The next topic we are going to start is the block diagram. We have multiple methods for modeling a system. Block diagram is one of them. We have already discussed the differential equations to model our systems. Control engineers usually use block diagram to model a system. Block diagram can model all types of systems. It can model linear as well as non-linear systems. Other methods are using the differential equations and the signal flow graph we'll see later. And the objective of modeling is to find the transfer function by which we can control our output. In this topic, we'll see some basic definitions with examples. We'll see the construction of the block diagram. We'll see some reduction techniques, and we'll see some examples or problems. How we'll apply these reduction techniques to find the transfer function from a block diagram. Block diagram describes the composition and interconnection of a system. It also gives the cause and effect relationship throughout the system with the transfer functions. Block diagram may have mathematical quantities, or sometimes it may not have mathematical quantities, but it simply describes the composition and interconnection of multiple elements connected in the systems. And already we have discussed that it can model linear as well as non-linear systems. Any specific configuration of the block diagram may have these four elements. These four elements are blocks. Blocks are the main points in which the transfer function is written, sometimes in words or sometimes in mathematical form. When we use block diagram reduction techniques to find the transfer function of a block diagram, or we want to model our system by the block diagram, usually we use S-domain transfer functions within the block of the block diagram. Otherwise, we can explain some basic descriptions. We can name some blocks. These are the fundamental element of the block diagram. Then we have summing points. These summing points actually sum the signals coming towards any point. These summing points actually simply represented by a circle. And the takeoff point are those points in which single signal is transmitted to more than one point. For example, here the output signal Z is transmitted to 2 points A and B. And these arrows are unidirectional, showing the direction of the signal flow. Canonical form is defined as the simplest form of the feedback control systems, in which we have a forward path and a feedback loop. We have a single forward path with the forward path transfer function G of S, and the single feedback loop with the feedback transfer function H of S, where R of S is the reference signal or input, and C of S is the output of the control system. This is the simplest form of the block diagram, which is called the canonical form of the block diagram. Usually we convert our complicated block diagrams into the simplest or the canonical form. In this diagram, R is the reference signal or input to the system, and C is the control variable or the variable which we are going to control. This is usually the output of the system. E is the error signal, which is actually the difference of feedback signal B and reference signal R. G is the forward transfer function, and capital H is the feedback transfer function. We use this canonical form usually to find the transfer function of C upon R, that is output upon input of any control system. This transfer function actually we use to control the output C. We can write C equals to input multiplied by transfer function, so we can control this we can control our output variable by using the transfer function. These are three different ratios we used from the canonical form of the block diagram. This is the control ratio C upon R, error ratio E upon R, and the primary feedback ratio B upon R. The simple derivation of these three ratios are given here, in which we use the simple definitions, and as it is very clear from the diagram that C is equal, that is the control variable or output, is actually equals to capital G into E. This is actually coming in cascade, so we are multiplying G into E, and the value of E is actually the difference between R and B. So we are just putting the value of GR minus GB, and we have solved it by putting the value of feedback signal B, which is equal to H into C, coming in series from the output side, and we have obtained the relationship G upon 1 plus GH, that is equals to C upon R, the control ratio. We use this control ratio to control the output variable C. For a known input, for example, if R is a unit step function, we can put the value of R and we can find the value of G upon 1 plus GH. We can adjust the values of G and H to find a required C of S for which we want to design the system. The second is the error ratio, which is again a simple derivation. We have just used the definitions of the error signals and feedback signals and controlled variable, and then we have obtained a relationship for E upon R, which is 1 upon 1 plus GH. And similarly, the feedback ratio is B upon R. Again, we have used the simple definitions of feedback signal and control variable and error signal, and we have obtained the value of B upon R is equals to GH upon 1 plus GH. These are very simple ratios. We use control ratio to control the value of controlled variable C. We can use the error ratio to find and adjust the error E or the feedback B by using feedback ratio. In all three ratios, we can see that 1 plus GH is the denominator, which is actually the characteristic equation of the system. We can use this characteristic equation in multiple solutions like stability. We'll see in the next lecture, inshallah, next 1 or 2 lectures. So 1 plus minus GH is equals to the characteristic equation. Please note that if we have a plus or a positive feedback, then we will have a negative sign in the denominator or the characteristic equation. Here in the diagram, you can see that we have used this with the summer minus plus sign, and in the answer we have used plus minus, that is actually the reciprocal of the sign in the canonical form. So in the characteristic equation, actually if we have a negative feedback, then it will be 1 plus GH equals to 0, and if we have a positive feedback, then we'll have 1 minus GH equals to 0 as a characteristic equation of the system. We'll use this characteristic equation later on in the different lectures. Now we'll see how we'll construct the block diagram. We'll see an example of separately excited DC motor. We have already modeled this DC motor while we were modeling our system by the differential equations. Now we'll see how we'll write these differential equations of the system, in the form of the block diagram. We have already discussed in detail the differential equation of the DC motor. Now we'll see how we'll convert it into the block diagram. This is the diagram of a DC motor. I hope you have remembered that we give an input voltage to the armature of the voltage, and we get a shaft rotation at the output. So here Tm is actually the motor torque, and if we connect a load to the motor shaft, then it will be represented by TL or the load torque, where this is the armature circuit RA, and LA is the armature resistance and inductance, IA is the armature voltage, and EA is the applied voltage at the armature, and displacement and velocity are respectively represented by theta and omega, where J is the motor inertia, Bm is the friction coefficient, and Ki is the torque constant. We will see the equations now. These are the equations of the DC motor. The first is the armature circuit. It is clear that EA is equals to IARA plus LADIA plus EB, and if we take the Laplace transform, then we have simply replaced D by R, and we used capital letters for the S domain. So EA equals to IARA plus LASIA plus EB. Similar, and if we take IA at left hand side, it will become 1 upon RA plus SLA EA minus EB. Next is the torque motor, which actually depends on the armature current, obviously. K and phi both are constant, flux is constant, so we have taken it as 1 K1, one constant K1. Equation will become Tm equals to K1 IA, EB back EMF is actually equals to KB omega n. KB is again constant for the motor. And if we write in S domain, we'll take the Laplace transform EB equals to KB omega n. Then motor torque equation will be equals to JD square theta m plus B theta m. And if we include TL, we can include it here with the motor torque plus TL. And if we write it in terms of the omega or the velocity, angular velocity omega m, then we can write it as Tm equals to JD omega m plus Bm omega m plus TL. And if we take the Laplace transform, we simply replace the sign of omega in the S domain, otherwise it is the angular velocity, the same angular velocity. So we have, or if we have taken omega m or the angular velocity at the left hand side, the equation will simplify it as equation 4. As we know that theta equals to omega upon s, this is the relationship between angular displacement and angular velocity. We'll use it while we draw the block diagram. So we have actually 4 equations here which we'll use to construct the block diagram of the DC motor. This is the summary of the 4 equations we have just derived. First is for IA. As you have remembered that IA is the output, and which we have actually written in the left hand side of the equation, and EA minus EB is actually coming from the input side. So this is actually the summer which is actually giving us the EA minus EB. You can see that there is a negative sign with the EB or the back EMF. So this is actually equal to EA minus EB. So the block is 1 upon RA plus LAS. So you can see here that IAS is the output of this block, and the input is of this block is EA minus EB. That is with the use of a summer, we have actually produced here EA minus EB, and the transfer function in the block diagram is the armature circuit values, 1 upon RA plus LA. In the second block, the output is Tm and the input is Ia. So we have developed another block with the transfer function within the block is Ki, and input is Ia, Tm is the output. And if we include the load torque, we will include it at this point. Right now we are actually considering the direct value of the torque, motor torque, and not considering the TL. So the next equation is EB equals to KB omega m. So omega m is the input at this time, and EB is the output. So we have taken is in the back EMF, as we know that the EMF, that the back EMF is actually using to self-control this motor. So EB equals to KB omega m. KB is the transfer function, omega B is coming from the input side. The fourth equation in which the Tm minus TL is actually the input. So if we have put a negative sign with the TL, Tm minus TL is actually working as an input. 1 upon JMS plus Bm is actually the transfer function for the motor. This is inertia and viscous friction coefficient Bm. Omega m, and as domain we have used its symbol as like omega. So this block is actually coming from the fourth one. If we are going to use this motor for the velocity control, then we'll leave it here taking omega m or velocity as an output. But if we are using it to control the speed or the displacement, we'll take the output variable as theta, which is the angular displacement. So we'll convert this velocity into the displacement using the block of 1 upon s. So if we are taking angular displacement theta as variable, we'll as the output variable, then we'll use theta as output variable. Or if we are using velocity as to control velocity, then we'll take the velocity as an output variable. You can find theta m, that is the angular displacement upon EA transfer function, simply by simplifying this block diagram. I hope you will be able to solve this block diagram after this lecture. And you can also find velocity upon EA or omega m upon EA by using this block diagram if you want to take out velocity as output variable. So I've just written the theta m upon EA, the expression for theta m upon EA. You can also evaluate it for omega n upon EA. Next, we'll discuss some block diagram reduction techniques. By using these techniques, we'll convert our complicated block diagrams in simplest or the canonical form to get the transfer function of the system. This is the first technique, combining block in cascade. When we have two or more blocks in the cascade or in series, we simply multiply the two transfer functions within the blocks. So here the output variable y is equals to the multiple of p1 and p2 multiplied by the input, that is x, because these are connected in series or cascade. So we can combine these two blocks by multiplying their transfer function p1 and p2 in the single block. So it will become y is equals to p1 p2x. The important thing is that whenever we apply some reduction technique, before and after transformation or the reduction, the expression for the variables should remain same. For example, here before the transformation we have two blocks p1 and p2 separately. Output variable is p1 p2x, and similarly we have converted into single block p1 having the transfer function p1 p2. Again the value of the output variable is y equals to p1 p2x. So this is the rule that whenever we apply some reduction technique or the transformation technique to simplify the block diagram, our value of the variables should remain same before and after the transformation. The second technique, if we want to combine some blocks in parallel, then in the first diagram there are two blocks p1 and p2 which we are actually connected in the forward direction, that is combining blocks in parallel. You can note here that the summer or the circle is in the right hand side of the block diagram. So y equals to p1 plus minus 2p p2 x, p1x plus minus p2x. Similarly, if we have this summer in the left hand side of the block diagram, usually it is a feedback path. We'll see in the next transformation. So here this is actually a forward path again. The signal is actually y equals to p1x plus minus p2x. p2 is already here in series with the x, so it is p2x. We can simplify it in two manners. Either we can simply add these two blocks p1 plus minus p2, or we may have a single block in the forward path in the main line p1 upon p2. You see here that p1 upon p2 and p2 both blocks are in series. So when we use p1 upon p2 multiplied by p2x, it will again become p1x. And similarly at the same manner when p2 is actually multiplying by x. So again the equation for both transformation will remain same, that is y equals to p1x plus minus p2x. The second technique, if we want to combine some blocks in parallel, then in the first diagram there are two blocks p1 and p2 which we are actually connected in the forward direction, that is combining blocks in parallel. You can note here that the summer or the circle is in the right hand side of the block diagram. So y equals to p1 plus minus 2p p2 x, p1x plus minus p2x. Similarly, if we have this summer in the left hand side of the block diagram, usually it is a feedback path. We'll see in the next transformation. So here this is actually a forward path again. The signal is actually y equals to p1x plus minus p2x. p2 is already here in series with the x, so it is p2x. We can simplify it in two manners. Either we can simply add these two blocks p1 plus minus p2, or we may have a single block in the forward path in the main line p1 upon p2. You see here that p1 upon p2 and p2 both blocks are in series. So when we use p1 upon p2 multiplied by p2x, it will again become p1x. And similarly at the same manner when p2 is actually multiplying by x. So again the equation for both transformation will remain same, that is y equals to p1x plus minus p2x. Here in the second transformation, we can see that our forward path is actually replaced by a single line. It means that its transfer function is 1. So this is, if when we simplify this, it will become P1 upon P2 plus 1 multiplied by x, and P2 is already multiplied by x is already multiplied by P2. So this will become y equals to P2 multiplied by P1 upon P2 plus 1 into x, and then when we open this bracket and simplify, we'll get y equals to P1 plus minus P2 into x. Here in the second transformation, we can simplify it as the forward path and a parallel forward path with a transfer function 1. When we directly connect some points, it will have a transfer function of 1. So it is P1 upon P2 plus 1, and this whole is actually multiplying by the series combination of P2 and x. So we'll multiply P1 upon P2 plus 1 by P2x, and when we expand this bracket, it will become y equals to P2 multiplied by P1 upon P2, so that P2 will be cancelled, and plus P2 multiplied by x, and it will become y equals to P1 plus minus P2 into x. So the transformation before and after the value of y will remain same. So we can apply this method too, although the first method is most popular, and usually we use the first method, but we can use the second method too if we want. This is a very important transformation in which we actually eliminate a feedback loop. The transfer function is g upon 1 plus gh. You already know we have derived c upon r equals to g upon 1 plus gh. So in this case, p1 is g and p2 is h. So the transfer function will be g upon 1 plus minus gh. Again, the sign in the denominator is actually the reverse from the block diagram. So we can again simplify it in two ways. Although the first one is the most popular easy way we use to simplify, but sometimes if we use a unity feedback system, then we can convert it in by the second method, in which we have P1 P2 in the major line, and we have input multiplied by a transfer function 1 upon P2. So again, in both cases, the output variable y is equals to P1 into x plus minus plus P2y remains same before and after the transformation. So in the transformation 2 and transformation 3 both, the first solution is the more useful and the more frequently used, but we can use the second transformation method too in both cases. This is a very important transformation in which we actually eliminate a feedback loop. The transfer function is g upon 1 plus gh. You already know we have derived c upon r equals to g upon 1 plus gh. So in this case, p1 is g and p2 is h. So the transfer function will be g upon 1 plus minus gh. Again, the sign in the denominator is actually the reverse from the block diagram. So we can again simplify it in two ways. Although the first one is the most popular easy way we use to simplify, but sometimes if we use a unity feedback system, then we can convert it in the by the second method, in which we have P1 P2 in the major line, and we have input multiplied by a transfer function 1 upon P2. So again, in both cases, the output variable y is equals to P1 into x plus minus plus P2y remains same before and after the transformation. So in the transformation 2 and transformation 3 both, the first solution is the more useful and the more frequently used, but we can use the second transformation method too in both cases. Here in the B part, we can see that we have simply replaced the feedback path with a unity feedback path, in which we have removed the feedback block and inserting a block 1 upon P2, which is the reciprocal of the feedback transfer function with the input x. We can prove it simply. The rule is again that we should get y equals to P1 into x minus plus P2y after the transformation. So if we start from the second diagram, that is the bottom right, we have marked intermediate point z here. First we'll find y upon z, that is output upon input, using the simple control ratio formula c upon r equals to g upon 1 plus gh. So here g is p1 p2 and h is 1. We are simply solving it for a negative feedback. So we have put here a positive sign in the denominator. So y upon z is p1 upon p2, 1 plus p1 p2, because h is here 1. If we simplify it as y equals to the transfer function multiplied by z, then we can simply put z equals to 1 upon p2 into x, because the value of z is here the simple series combination of 1 upon p2 multiplied by x. So in the next step we have put z equals to 1 upon p2 x, and when we keep x in the denominator in the left hand side, y upon x equals to p1 upon 1 plus p1 p2, where p2 is cancelled in the numerator and denominator in the previous step. And when we simplify this last equation, we'll get y equals to p1 into x minus p2y, which is the same equation for the first diagram. So before and after the transformation, the expression for the control variable y is same, and we have simply used the formula of g upon 1 plus gh, that is the control ratio. So we can use this transformation too, but usually it is a common practice to reduce the diagram or eliminate the feedback loop by the first transformation, in which we have simply replaced this feedback loop by a single block with the transfer function p1 upon 1 plus minus p1 p2. Next transformation is moving a takeoff point ahead of a block. Here the output variable has a value p into x, and we are transmitting the output value y to 2 points. A takeoff point is actually, or sometimes also called a pickoff point, where a signal is transmitted to more than one point. So after the transformation, if we want to move this point A ahead of the block P, then the value at the point ahead of the block will become x. So we have to multiply it by a block P. So now at both point y, the value of the signal is px. So we can move this takeoff point ahead of a block by multiplying this block by p. In the next transformation, we are moving this takeoff point beyond the block. So point B is actually moving here. So then please note that here the signal x is actually transmitting to 2 points, where in the previous transformation the output variable y is transmitting to 2 points, to 2 different points. So here x is actually transmitting, and if we are moving point B beyond a block, then the signal at point B will become px. So to cancel it, to cancel this p, we multiply this by 1 upon p, so that the signal will again become px. So at both points the signal x is transmitting and y will remain same, which is equal to px. Next transformation is moving a summing point ahead of a block. So here we simply move the summing point ahead of a block. The value of z before the transformation is px plus minus y, and it is clear from the diagram that it is multiplied by p, so we have divided by p2. Again the expression will remain same, z equals to px plus minus y. Next transformation is moving a summing point ahead of a block. So here we simply move the summing point ahead of a block. The value of z before the transformation is px plus minus y, and it is clear from the diagram that it is multiplied by p, so we have divided by p2. Again the expression will remain same, z equals to px plus minus y. Here again in the second transformation, we can see that z is the sum of the two signals by a summer, because we have moved this point, summing point. So the z is actually the sum of the two signals. The one is simply x, and the another one is 1 upon p into y, because y and 1 upon p is both are in series. So there is this is whole is multiplied by p. So z equals to p into x plus minus 1 upon p y, and when we expand this, we open the bracket, we'll get y z equals to px plus minus y, which is the same expression before the transformation. So this time again we can use this transformation. The output variable z will remain same in both cases. The same theory applies here when we move a summing point beyond a block. So this time we have multiplied the block by p to get the same value, that equals to p into x plus minus y. The same theory applies here when we move a summing point beyond a block. So this time we have multiplied the block by p to get the same value, that equals to p into x plus minus y. Here we can see that when we move the summing point beyond of a block, the signal coming at point z is the sum of the two signals. The one is x, which is multiplied by p, a block p, and y is also multiplied by, we have also add a block p with the signal y, so that the signal z will remain same. So we can see here that in the rightmost diagram, z is equals to the sum of px, this is a plus sign, and a plus minus sign with py. So z equals to px plus minus py, and when we simplify it, it will simply become p into x plus minus y, which is the same signal before the transformation. So we can use this transformation whenever we need it. If we want to move a takeoff point ahead of a summing point, again the rule is same, that the value should remain same. So we have introduced one more summer, and we have moved point B to ahead of our summing point, and the expression in both cases will remain same. At any point the value of z equals to x plus minus y, and the value of x and y is same as x and y before and after the transformation. Now this time takeoff point B is shifted beyond the summing point, and again the expression z equals to x plus minus y will remain same before and after the transformation. Sometimes we need to rearrange some summing points. So we can rearrange in two different methods. In each case, the value of z will remain same before and after the transformation, that is equals to w plus minus x plus minus y. We can use in either way. We can use in any transformation A or B if we want to rearrange the summing points. Now the steps of the block diagram reduction. Usually we first combine the cascaded blocks. If we have some blocks cascaded in the block diagram of the system, then we first combine these blocks, and then usually we combine all the parallel blocks using second transformation, so that our block diagram will become more simpler. Then we try to eliminate all the minor feedback loops, and then we'll try to move summing points to left and takeoff points to right of the major loop. Then we again repeat these steps to find the canonical form. But please keep in mind that these are not very hard and fast. Sometimes we analyze the given block diagram, and we can alter the order of these steps. We can alter the order of these steps if we find it easier and convenient. We can change. We can see the diagram, and we can apply these rules in any other order to get the simplified form. Otherwise, usually we use these steps to reduce the block diagram to the canonical form. Now we'll see the first problem. Reduce the block diagram into the canonical form by using the reduction techniques. In this problem, first we are watching here that G1 and G4, these two blocks are in cascade. So we multiply the block diagram using the first transformation. So it will convert into a single blocks G1, G4. In the second step, these G2 and G3 are connected in parallel. So we'll use transformation 2 to combine these two blocks, and we'll simply add G2 plus G3. And then we see that we have a minor feedback loop G1, G4 with a feedback H1. So we'll use the third transformation. G1, G4 is a feedback loop. Using formula G upon 1 plus GH, we'll get this G1, G4 upon 1 minus G1, G4 H1. And then this two blocks are combined in series. Will combine in series. So it will become G1, G4 upon 1 minus G1, G4 H1 multiplied by G2 plus G3, and then again it will convert into a canonical form with a single forward path transfer function G of S and a feedback transfer function H2. Now the Gaussian block diagram is converted to a simple canonical form in which we can put the value of G and H in the expression C upon R equals to G upon 1 plus GH to find the closed loop transfer function C upon R. Now the block diagram given in the question has been converted into the canonical form in which we can put the value of G and H in the closed loop transfer function expression C upon R equals to G upon 1 plus GH, where G is G1 G4 into G2 plus G3 upon 1 minus G1 G4 H1 and H is equals to H2. We'll put the value of this G and H in this expression to get the closed loop transfer function C upon R. You can complete it at your own. Now this is the second problem. Again we have to apply the reduction technique to find the transfer function. This time we have multiple feedback loops. We'll simplify this diagram. In this diagram we have first simplified the summing points. So we have converted these three loops into single loop with the transfer function adding and subtracting respectively H1 minus H2 plus H3. And then this is the we have simplified the loop G2, G3 and feedback path at H1 H minus H2 plus H3, and then it is in cascade with G1. And then the next step we have find the open loop transfer function C upon R as given in the diagram. Problem number 3, reduce the following system to a single transfer function. This is the block diagram given for a control system. Here in the diagram, after solving the two problems, we can see here that at the rightmost loop G3 and H3 can be solved, but the second loop G2 and H2, in which the forward transfer function is G2 and the feedback is H2, cannot be solved directly because of the point V3. So if we move this point V3 beyond the block G2 towards V4, then it will G2 and H2 will become a loop. So we'll move this point V3 to beyond the block G2, and then this will become a parallel path with the transfer function 1 and 1 upon G2. I hope you can understand this transformation. If we have a feedback transfer function, or if we have a feedback loop without any block that is directly connected output to input, then it means that h of s equals to 1. Similarly here, if we move point V3 beyond the block G2, then in the next right parallel path, if we combine this parallel path using transformation 2, combining blocks in parallel, then the major line will have a transfer function 1, and 1 upon G2 will be the second path. So the transformation will be 1 plus 1 upon G2. We'll solve it in the step by step in the later slide. Now after discussing the problem, I hope you can understand it better. In the first step, we have simplified the rightmost loop using the transformation eliminating a feedback loop, and we have moved point V3 beyond the block G2 by multiplying or by adding a block 1 upon G2 in the forward path, in the parallel forward path. Then in the next step we have step 2, we have eliminate we have combined the parallel path 1 upon G2 plus 1, and then next step is very clear because we have combined cascaded blocks in the rightmost side, and we have added the summers as we have done in the last problem. It is a simple feedback loop, and we have simplified this using the transformation, eliminating a feedback loop. And then is step number 4, these two blocks in series, so we have combined blocks in series by multiplying their transfer function. So we have a simplified transfer function as a single transfer function for this diagram. Okay, this is the next problem after simplifying 3 block diagrams. We can solve this block diagram too. We can see here that the first minor loop with the forward transfer function G3, G4 and feedback transfer function H1 cannot be solved because of the point X in between G3 and G4. So it means that to solve this feedback loop, first we have to move this point X beyond the block G4. If we move this point X beyond the block G4, we have to add a block 1 upon G4 cascaded with the block H2. So we can solve it step by step, and you will see that first we'll move this point X beyond the block G4, then we simplify the first minor feedback loop, and then in this next stage we'll find the simplified block diagram. So as we have just discussed, first we have moved in the first step point X beyond the block G4, and then we have added a block 1 upon G4 with the block in series with the block H2, and we have cascaded these two blocks, combining by multiplying their transfer function H2 upon G4. In the next step we have simplified the first and the rightmost feedback loop, and then we have G2, G2, G2 and G1, G4 upon 1 minus G1, G4, H1 with a feedback loop at the upper side with a negative feedback sign, and in this case H of S is H2 upon G4, and we have simplified this minor feedback loop. And in the step 3 we can see that we'll simply combine the first two blocks in series G1, G2, G3, 4 upon 1 minus G3, G4, H1 plus G2, G3, H2, and then we'll get a simple canonical form, and we can find the open loop transfer function also here. So I hope this is quite clear to you. I advise all of you that to solve these problems by hand also. I hope all the steps are clear now. So I advise all of you to do these problems by hand.